So a chemical reaction involves a rearrangement of the way that atoms are grouped together. A substance is being destroyed, but the atoms that form the substance are not being destroyed. They're just being rearranged. And we use a chemical equation to represent a chemical reaction, just like we use equations in math to represent something that's happening. So here's an example of a chemical equation. The chemical equation is in black. CH4 plus O2, and there's an arrow, CO2 plus H2O. The arrow is a lot like the equal sign in a mathematical equation, except it does indicate a direction. So on the left side of the arrow, we have the reactants, and on the right side of the arrow, we have the products. The reactants react to produce the products. So these things react, and the arrow points to what gets produced. So the atoms are not created or destroyed. They're just rearranged. So any atoms that are present at the beginning in the reactants must also be present in the products. It's a little bit like playing with Legos. You know, you get out a couple handfuls of Legos and you build something. And then you take that apart and you build something different. All the Legos that you started with are still there. Contrary to the belief of some of my children, Legos do not disappear into thin air. Okay? And sometimes I feel like they come out of thin air because you're walking in the dark and you step on one barefoot and you go through the ceiling because those little suckers hurt. And they're all over my house. But they were just hiding. They were like in stealth mode or something. It's not that they just come out of nowhere. And atoms don't either. So I find it helpful to think of atoms rearranging a lot like Lego blocks. So we have the same number of each type of atom on both sides of the arrow. So let's just draw a little picture here. Just because we can. What color? Let's do green. So say we have something like that, two little green blocks. It's not a very good Lego color, but whatever, right? Come on. Oh. And so we've got two 2x2 dark green Lego blocks, and we've got two 2x4 light green Lego blocks. And we're going to rearrange them. Okay, we don't have things appearing or disappearing, so we could write a little Lego equation here. When we take those apart, we can't just have some of them and not the others. So maybe, that's not what I meant to do. That's not what I meant to do either. This is not working the way I want it to work. Which is, how life kind of goes most of the time. Could we do that? Could we take two dark green bricks and two light green bricks and make this and not have anything left over? No, we can't. There's going to be two more bricks left over. So all the bricks that we started with have to end up, they're still there in front of us. So we could end up with two of these things, right? Well, that's not very good. So we built something else. We could end up with two of those. But what we start with has to be present at the end. So we talk about balancing a chemical equation. So CH4 is not a compound we've learned how to name, but that's methane, that's natural gas. And O2 is oxygen. And if we burn if we burn methane, we react it with oxygen, it forms carbon dioxide and water. But let's look at the individual atoms that are present here. So in this circle, we have the atoms that are in methane, one molecule, one carbon and 4 hydrogens. And over here for the oxygen, we have 2 oxygen atoms. This is one of those diatomic molecules. In CO2, one molecule has 1 carbon, 2 oxygens, and 1 molecule of water, 2 hydrogens, and 1 oxygen. Now, if we tally these all up, in our reactants, we had 1 carbon, 4 hydrogens, and 2 oxygens. And then over here in the product, we've got 1 carbon, 2 hydrogens, and 3 oxygens. Okay, that's not possible. You can't have 2 hydrogens just disappearing, and you can't have an oxygen atom just appearing out of nowhere. And you also can't change 2 hydrogens into an oxygen. So this can't be describing exactly what's happening. So we need to balance the equation to account for all the atoms that are present in the reactants and the products. The reaction does what it does. We are just describing what happens. So when we look at these totals here, we see that we don't have enough oxygens in the reactant to account for the oxygens that show up in the product. So if we put in another oxygen molecule, now we have a total of 4 oxygens. And here we had 4 hydrogens, and over here in the products we only had 2. So there must be more hydrogens somewhere. So if we add another water molecule, that'll give us a total of 4 hydrogens. Just like we had to build another little stupid thing with the 2 blocks. That's pretty lame Lego building. Where was I? So if we throw another oxygen into the equation and another water molecule into the equation, now we see that we have 1 carbon on each side. We started with 1 carbon, we end up with 1 carbon. We started with 4 hydrogens, we end up with 4 hydrogens. We started with 4 oxygens, we end up with 4 oxygens. All the atoms have to be accounted for in the chemical equation. And then we call it a balanced chemical equation. So you can envision this as being a little Lego creation with 4 H blocks and 1 C block. And you're taking it apart and you're putting it back together. And now you're putting the H's with O's and the carbon with O's. You're just rearranging the blocks. But the blocks that you started with are still there. Any questions? So what we call the balanced equation is that we have 1 methane molecule is going to react with 2 oxygen molecules. So this is just a description of this picture here. 1 of these and 2 of those. And that will form or produce 1 carbon dioxide molecule and 2 water molecules. Many times in the chemical equation, we indicate the physical states of the reactants and products. Sometimes this is important, sometimes it doesn't matter, but we do need to understand what these symbols mean. So to indicate the physical state of a reactant or product, we put a state, we call this a state symbol, after the formula. So S stands for solid, L stands for liquid, G stands for gas. That's, just the first letter. And then there's this other one, AQ. And AQ is the first 2 letters in aqueous, which is similar to the Spanish word for water, agua. It's just the Q has its tail turned backwards. So aqueous solution means that this thing is dissolved in water. So anytime you see AQ, it means that whatever substance that is, it's dissolved in water. So here's an example of a chemical reaction. Here we have solid potassium metal. So we have K and then S in parentheses after that. So that's telling us that the potassium is a solid in this reaction. And we're reacting it with water in the liquid state. If a temperature or other conditions are not specified, then we assume that it's at room temperature. So this is something that would happen at room temperature. And by the way, this liquid here is not water, it's actually mineral oil, because potassium reacts with the moisture in the air. But pure potassium metal is this shiny, cool looking shiny substance. If we put this into a beaker of water, something very interesting happens. We see some little bubbles forming. That's evidence of a chemical reaction. So hydrogen gas is being released. It's in the gas state. And the other parts that are left form an ionic compound, potassium hydroxide, and that's dissolved in water. And what's this red stuff here? That's a flame. This generates so much heat that the hydrogen gas spontaneously combusts. So you can imagine you don't want to put too much potassium in water because you could get an explosion. Sodium will do that too. It's kind of dangerous stuff. And that's why, there are different kinds of fire extinguishers, because there are some types of fires that if you throw water on them, you're going to make them a lot worse. If you've got sodium or potassium, you don't want to throw water on it. That's going to cause a fire. Yes? Francium? Francium would probably react as well. But francium is radioactive and unstable, so good luck getting a hold of any of that. Any other questions? Let's look at this equation. Is this balanced? How many potassium atoms are shown on the left side? Just one, right? And how many potassium atoms are over here? There's just the 1K here, right? So we've got 1K on this side and 1K on that side. How many hydrogen atoms are shown on this side? 2. And how many are shown on this side? 3. This isn't balanced, is it? Because here's 2. Those could have been these 2, but then where does this one come from? And here's an oxygen, and there's an oxygen. So this is not a balanced chemical equation. But it is an equation that describes what happens. Yeah, we'll have to do some things, but we're going to learn about balancing equations in the next section. So here's an example. When blue light shines on a mixture of hydrogen and chlorine gas, the elements react explosively to form gaseous hydrochloric acid. What is the unbalanced equation for this process? And they're asking for the unbalanced because we haven't discussed how to balance it yet. So we look at these choices, and we have to, this is like making up a math equation to describe something that happens. If Johnny has 5 apples and Susie has 3 apples, how many apples do they have together? And then you say 3 plus 2 equals 5, right? So this is the chemical version of that. So we look at the sentence, we've got a mixture of hydrogen and chlorine gas, and those elements react explosively to form, so that's the arrow. So we've got hydrogen and hydrogen plus chlorine react to form, there's the arrow. Actually, I'm going to write that on there. So hydrogen plus chlorine form, yeah, that's not what I wanted at all, to form hydrochloric acid. So then when we're looking at these, we're looking for hydrogen and chlorine. That's not chlorine, is it? Okay, so that one's not right. Here we've got, that's not hydrogen and chlorine either. That one can't be right. So this one, hydrogen and chlorine, okay, maybe. So we've got 2 of these that both have hydrogen and chlorine. Let's look at the product. We've learned how to name and write formulas now. Hydrochloric acid. That's a binary acid. It's got hydrogen and chlorine. Chlorine from the periodic table we see has a -1 charge, and so the formula for that is HCl. So both of these are HCl, and that's correct. And then there's state symbols given here too. It says hydrogen and chlorine gas, and it forms gaseous hydrochloric acid. So all these state symbols are correct. So the difference between these two is this one has just H and Cl, and this has H2 and Cl2. Which one's correct? Horses need oats for clear brown eyes. It's D. Hydrogen is a diatomic element. When hydrogen is by itself, not in a compound, it always forms a molecule of 2 atoms. Chlorine is also a diatomic element. So that sentence, horses need oats for clear brown eyes. H in horses is for hydrogen, and the Cl in clear is for chlorine. So this is the correct unbalanced equation. Any questions? I don't know what that one's about. That one was blank.